scale, or almost at scale. And mostly, I think, what we need to take away is how small the region that is so crucial is, right? And we tend to neglect everything underneath, but the support does impact the transport. So again, questions that come to mind are, what does the support look like structurally? Are the pores random? Are they periodic, right? When you look at the actual film, there are pores. For years, people thought these were artifacts, but these are real pores. The polymer encloses these voids that are liquid filled under operating conditions, so they impact transport quite considerably. And again, the baseline for a lot of this work was, let's just model this as a diffusion problem. A diffusion problem in steady state is just solving a Laplace equation. Laplace equations are dominated by the boundaries. So really, when you play around with the way that the boundary is distributed, whether it's the support, whether it's a pore, whether it's a periodic structure that has an equal thickness everywhere, or maybe we use these wavy sinusoidal structures, which are obvious idealizations, but they do give you the idea that some areas are thinner, some areas are thicker. Or we introduce voids into these structures to see what happens when you start poking holes in them. And again, very idealized structures that I wouldn't think look anything like a real membrane, but on the other hand, provide a lot of insight. So to really rush through this, because this really isn't the point, here's a really idealized structure. It's just a thin film over pores. But it does tell us two things. A, and this has been corroborated experimentally since the first theoretical papers were published. If you take the same thin film and you cast it over different supports, you are going to get a different membrane. And that membrane will be better if you tailor the support to have, I really kind of have to narrow it down, lots of little pores. That's what's good. And in this case, we also looked at the question of, all right, what if the support is this phase-inverted, random, messy thing? Do I really want to go through the trouble of making a periodic structure? And the answer is sometimes. So if you look at the deviation between the idealized, the red and blue lines, these periodic structures, and the random structures, there are regions where the gap can be, I guess, about 20, possibly 30%. So you have to ask yourself, is that important enough for me? And if it is, then you go through the trouble and you make a support that is periodic. But if it's not, then you settle for what you have. And then the question is, what's easy to obtain? The second thing is, if you can make a support that isn't completely impermeable to the solute or the water, then you can really improve the membrane. And when you think about, early phase inversion cellulose acetate RO membranes, they were like that because the dense film and the support were the same material. But today, we use different polymers, and polysulfone, for example, is not a very good support if you want transport to occur through the solid phase. So I think there's some room for improvement there, and people have already started playing around with other polymers that are more hydrophilic. So a lot of this has translated into experimental work, and it's been a lot of fun for me over the years to see people following it through experimentally. And when you dive into the film itself, this will be the last slide for this today. A bunch of really nice images that tell a very important and very recent story. Polyamide is nothing like a homogeneous film in terms of transport. There are holes in it. It folds over in different ways. Sometimes the fact that it folds over or becomes crumpled or bubbled, sometimes it's good for us. Sometimes it isn't. If you go too far, you start destroying the good capacities. And so it's been an interesting question, and I think an ongoing question, to try and highlight what would be the best structure. And here we also used this kind of idealized sinusoidal, so thickness variations, but we also put holes, and we asked, all right, does it matter where the holes are? And the answer is absolutely. So as you can see in this kind of image, if there are holes in the film or voids in the film that actually communicate directly with the permeate space, and this is seen in this model where we have this space, this yellow space in the middle, it's kind of a liquid. So it's not much of a barrier to transport. But if it's connected to the permeate space, and preferably via a pore in the support, then increasing this roughness, increasing the amplitude of this sinusoidal idealized structure actually translates into better permeance. So this age-old question of does roughness increase permeance is true in some cases. So it's true if the structure facilitates this type of transport. And as we've seen in experiments, sometimes you can have a very rough membrane with very, very poor performance because these conditions don't all conspire together. So what do we have? I think that I hope that I've shown you that simple models can teach us a lot. And by virtue of the simplified or the simplifications that are inherent to the models, we can do a lot with them. We can play a lot with them. We can probe a very large parameter space, and we don't need a really, really powerful computer to do so. And that's really the strength of it. But if we want to go into more predictive territory, we need more elaborate models, and more importantly, we need to bridge the continuum on molecular scale, because a lot of the interactions occur on a molecular scale, and we need to find a way to combine these models and, again, still be efficient. I want to leave you with a little bit of an image. So, because my last point here is to say that ultimately we also need to know how the morphology is generated and what are the realistic expectations for that. And you can see an image here running in the background of some experiments that we've been doing in my group of imaging, right? Because I'm a theorist, and if I do experiments, I want to see what's going on. So we use a lot of microscopy, and here you can see a polyamide film as it forms in a microfluidic channel under the microscope, and we're just trying to understand the dynamics of the system. Because I think that ultimately, to be able to properly inform the formation or the fabrication of the membrane, we have to understand its inherent limitations. Okay, and so I promised to say something about where do we go from here, right? So, yeah, I'll just skip over to this one. Yeah. So, how do we model real structures, right? I showed you this example where you take a real structure, you reconstruct it digitally, and you solve equations, and that can certainly be done. But I would say that I would only do that after I'm convinced that I have a very good idea for what the structure should look like. Before that, I want to see how general attributes affect transport. And one solution is a methodology called homogenization. It's a very, very nice, very powerful mathematical theory which falls under the category of asymptotic analysis. And it basically means if you can exploit some periodicity, usually in a system, then you can bridge over the scales. You can start with a small scale, but smear it over a larger scale, and then save a lot of computational time. We've done a little bit of this with respect to composites, and there's some very nice work out there from colleagues at Oxford on filtration membranes and how porosity gradients interact with transport. And I think that that's a very, very powerful tool that should be used more. But you have to think about how to adopt that tool to an existing situation or an existing structure. Molecular simulations, as I've said, they're more accessible than they used to be, but I really want to see measurable quantities coming out of simulations so that experimentally you can probe what the molecular simulations have done. And I don't mean measuring rejection or permeance. I mean truly molecular scale interactions as they are manifested at a scale that is measurable. I have to admit, I have some ideas, but I don't know that this is a straightforward thing, and it requires some crosstalk between experimentalists and people who understand what the simulations can or can't do. And then finally, the mesoscale, which is really where I feel more comfortable or more at ease. So one question is, how far can we push continuum models? And as I said, I'm a firm believer in the bulk property. So a bulk property is very well represented in continuum, but boundary interactions is really when it becomes hazy, and we have to be careful. And that's where we need to find a way to incorporate these interactions into a full membrane or a large scale model. And that's the same, that comes down to the same type of challenge that you have when you want to make sense of molecular simulations. So if molecular simulations can inform these mesoscale or subcontinuum models just by virtue of introducing boundary interactions into these models, I think continuum modeling can take us very, very far. And yeah, so I want to thank Andrea again for the opportunity to speak, and thank you all for the patience and the attendance. And I hope that we can do this again in person sometime soon.
Thank you, Guy, very much for a very interesting talk. Expected. Now, you did use your time, but there is a question from Antoine in the chat. I don't know, can you see it? Or should I read it out?
Let me just exit the share. I can probably see. So I'll read it out. The focus is now completely on the relation between structure and resultant flux, but the membrane structure certainly also determines mechanical properties. Should that not be taken into account, especially for it? That's a great question. And I think that it is receiving some attention, but definitely not as much attention as transport. And I think that that's a natural consequence of what the membrane is ultimately used for. But as anybody who's ever used an RO membrane knows, you lose up to 30–40% of your permeance in the first few hours after you compress the membrane. So yeah, mechanics play a role. If you can make a more robust membrane, and people have shown that this can be done, for example, using nanocomposites, then yes, then the robustness of the membrane will translate into better performance. And again, also when you change materials or when you change morphology, you have to think about structural integrity. So that this idea of finger voids in a membrane makes the membrane more open, but also makes it more amenable to compaction. So I'm not sure. That's the short answer, but the really short answer is yes, we should.
Okay, there's a hand raised, and that will be the last question, please. I have a list of questions, Guy, but we will do that separately. There is Yaqub Mansour Pana. Now, are you guys unmuting? Yeah.
Hello, can you hear me?
Yes.
Yes.
Thank you very much, Professor Roman. May you please share your slide about bridging the scale number 2? Is it possible?
You mean to show it on the screen now or to send
it? Yes,
yeah.
If possible.
Yeah, I can.
I didn't see about the number of the slides, so I can refer you to the number of the slide.
So you mean this one?
Number 2, bridge. Oh yeah, yes. You talk about the thickness, about the roughness and pores of the polyamide membrane here. Yes, you are talking about the simulation you did in this slide. What is important for me is to ask you about the correlation between the thickness and density of thin layer. It is very, very important for performance of the polyamide membranes. In this slide, and what are you showing in the next slide? I didn't see any data about the thickness of the polyamide membranes, and importantly, the correlation between the thickness and density of the skin layer. It's very important. I know that when you have a very thick polyamide film, some people believe that it is resist for the transportation of water from the skin layer, But
You need to move on, please.
yes, good. And you can consider and talk about the density and the correlation between the density and thickness of the polyamide, if possible.
So there's no quick answer to this, but I'll just say, yeah, you're right. But the main point of what I was trying to convey here is that the details that you're referring to all fall into the question of what is the material and what's the material property. And that's a very, very important question. The models that I showed you completely ignore it. So I'm just dealing with stuff, right? And the question is, how does this stuff get distributed in space? So it's all geometric. But definitely, one has to also look at what the stuff is made of. And by the way, the question of density also depends on whether this stuff or this film has pores or voids or crumples, or whether it's really a continuous homogeneous film. So I think that some of the things that you refer to are completely ignored here on purpose, whereas others are incorporated in kind of a backhanded way. So, but yeah, you point out very important questions.
Thank you very much. Thank you.
We have some more comments in the chat. Please look at them, but we have to move on. So I'm very, very thankful to Guy